Hello, everyone. Thank you so much for joining us this evening. Tonight, we have a tech talk on load balancing and horizontal scaling by Austin Fraser. Austin, whenever you're ready, take it away.
Okay, thank you, Ari. I just want to start out by thanking Pressable for sponsoring the Tech Talk tonight. Hey, everybody, my name is Austin, and tonight I'll be talking about load balancing and horizontal scaling. So let me start out with a quick story. So picture this. The year is 2013, and you're global pop superstar DJ Khaled. You're about to drop your new smash hit, I Want to Be With You, featuring Nicki Minaj, Future, and Rick Ross. But are the big digital music retailers ready for a hit of this magnitude? You pick up the phone. I'm on the phone with the CEO of iTunes, you say. I Want to Be With You has only been up for 1 hour and it's been selling like crazy. My staff is telling me the servers are about to shut down. I gave them the okay to add the most powerful servers to handle this. Thanks to your quick thinking, the single release went off without a hitch. So what's the lesson here? The CEO of iTunes and the rest of the team at Apple could have avoided this near disaster if they had only implemented horizontal scaling and load balancing in their system. So what is a load balancer? A load balancer is a solution implemented either as software or hardware that manages incoming traffic to multiple instances of the same service. This is done to ensure scalability, reliability, and optimal performance. So imagine a large and popular restaurant. The restaurant has a sprawling dining area. There's tables filling the space wall to wall. Tables are divided into sections, and a different server is responsible for each section. So load balancer is like the restaurant host. They're showing new diners to their table as they arrive. And imagine if the host just seated diners randomly without checking the availability of each table. Some sections would get overwhelmed, others would remain empty. The load balancer ensures that no server or no section gets overwhelmed. To deeply understand why load balancing is needed, we first need to explore the concept of horizontal scaling and the critical role it plays in application system design. So let's start with an example. So imagine we have a web application deployed on a single application server. So let's look at our day one. We launch our app and a single user logs in. So off to a pretty humble start. The server handles this effortlessly though. The CPU utilization and memory usage of our app server barely register. So let's look at our next day. Our app's gaining a little bit of traction and now 100 users are online. Server's still handling traffic, no problem. CPU utilization's at 30%, using about a third of the memory. But now let's look at our day three. So awesome, our app has gone viral and now we have 1 million concurrent users. Great, right? Well, we have a problem. At this point, the server has hit its limits. It's maxed out on CPU and memory. It crashes and now it's failing to respond to user requests. So this is catastrophic from a business point of view. What can we do to address this? One option would be to scale vertically or scale up by upgrading the server with more CPU and more memory. This would increase its capacity to handle that traffic. However, vertical scaling has physical limits. In other words, there's only so much processing power, only so much memory we can actually squeeze onto this one little physical box. Eventually, even the most powerful server is going to get overwhelmed. So instead, a better approach would be to scale horizontally or to scale out. So this just means adding more servers. Additional servers will get spun up and they replicate the same functionality as the first one, and that reduces the pressure on any one individual machine through the sharing of that load. Horizontal scaling is vital to an organization's cost efficiency. We only want to provision what's needed for the business at any given point in time and nothing more. This creates a new issue, however. When we have multiple servers performing the same functionality, how does our system know what app server to connect incoming client requests to? Load balancing is the solution. In our example, we would provision a load balancer right here in between our clients and our app server pool. Our load balancer will efficiently distribute the traffic to the servers to maximize the system capacity and minimize the time it takes to fulfill those incoming requests. Load balancers also play an important role in dynamic scaling, which is another important concept for horizontal scaling. Dynamic scaling, or auto scaling, is the ability to automatically add or remove servers to our system as the volume of inbound requests goes up and down. App servers can communicate to a load balancer and an auto-scaling service about their current usage. When traffic is light and an app server is under very little load, the load balancer and autoscaler can work together to detect this and automatically deprovision the extra servers in order to save on costs. By the same token, app servers can report that they're exceeding healthy limits of usage when they're under heavy traffic. They can signal to the autoscaler to scale out in response, to spin up more servers, so that the system can meet the rising demand and decrease the individual load. Let's say, for example, Nike announces a store-wide flash sale, or Beyonce drops a surprise album on Tidal overnight. The tech teams at these companies need to prepare for dynamic scaling in order to anticipate these large, sudden spikes of demand. So when we use load balancing to manage traffic efficiently, our application can benefit in three areas. The first is scalability. It allows our application to grow with the business and keep up with the user demand. Next would be increased reliability. Load balancers reduce our system's overall downtime and they make our system more stable. So users place more trust in the app when it's down less, and it makes them want to keep coming back for more. Lastly, it would be performance. The system's latency goes down through a more even distribution of traffic across the servers. In other words, the app just works better. Now that we understand what load balancers are and why we might want to implement them, let's examine how they actually manage traffic. A simple round-robin approach assigns each new request to the least recently used server. So if we had 4 servers labeled A, B, C, and D, we would assign the requests sequentially. First request comes in, we're assigning to server A. Next request comes in, we assign to server B, then C, then D, A, B, C, D, etc. Round-robin approach might work for a fairly simple application. Let's say simple internal tool, something where we're anticipating relatively low traffic. It's cheap and it's easy to set up. However, if some user sessions last a long time, we might quickly get lopsided numbers of connections across our pool of servers. So the issue with this approach, high level, is that our load balancer has no awareness of the load on each server when it assigns it a new connection. A smart balancing approach, on the other hand, features a load balancer that is aware of the server load. So here, app servers are constantly communicating back and forth with the load balancer about how busy they are. With each new request, the load balancer chooses the server that's currently under the least pressure at the time. So in our example here, we've got our server pool of 4 servers. First 3 are kind of hovering around 50% CPU utilization, but we have our 4th one, which is, it's only using 15%. New request comes in, we're assigning to this 4th one because it is most able to handle the request at that time. Another smart balancing strategy would be balancing by least connections. So a really similar approach, but instead of comparing CPU utilization, we're comparing just the raw number of connections per server. So again, server pool of 4, got a minimum of 1,000 connections on servers 1, 3, and 4, but server 2 only has 10. So it is most able to handle new connections from this point forward. That's where we're going to connect to. Smart balancing offers the best possible application performance, but it comes with a more complex setup, configuration, and is more costly. So we'd expect this kind of approach in a high traffic enterprise application, think e-commerce site, digital streaming platform, this kind of thing. So let's talk about how load balancing is implemented in the real world. Generally speaking, engineering teams don't design or implement their own load balancers. Instead, they'll use industry standard reverse proxy solutions such as HA proxy or Nginx to handle load balancing and other responsibilities bundled together. So let's consider a typical use case for Nginx. When implemented, it would serve as both load balancer and reverse proxy, combining those 2 roles. As a load balancer, it sits in front of our backend servers. It's distributing the incoming requests to them and doing so according to configurable rules. But it's also acting as reverse proxy. It's caching server responses, it's managing SSL termination, and it's providing additional security features. It's also important to remember that cloud providers often supply their own load balancing solutions. So let's say our application's hosted on AWS, you could easily integrate Amazon's own solution, Amazon Elastic Load Balancer. So what technical challenges can an engineering team face when implementing load balancing. So let's consider a massive application with global scale, millions of users. If all the clients in the world, they're all pinging this one load balancer with all their requests, the load balancer itself can become a bottleneck. Under high demand, load balancers can become single points of failure, and we definitely don't want this in our system. In such cases, we need to horizontally scale the load balancer itself. To solve this kind of problem, it would be typical to consider so that we're managing traffic regionally in order to minimize the network latency. So for example, we take all the clients who are coming from North America, we connect them to a North America load balancer so they get connected to North America app servers. The clients who are coming from Asia, same thing, connect them to Asia load balancer, then they get connected to Asia app servers. So we're minimizing the distance it takes those requests and responses or physically traveling to keep that network latency down. So I want to leave you with a couple of final thoughts. The bottom line is that we expect seamless user experiences, lightning fast performance, and 24/7 reliability from the apps and services that we love and rely on every day. Load balancers are the unsung heroes of this paradigm. By distributing traffic intelligently, they ensure that our systems are scalable, reliable, and performant, even under massive demand. Whether you're a solo developer building an app from scratch over a weekend or on a team scaling an enterprise-grade service, load balancing is an essential tool for keeping systems running smoothly. As technology evolves and the public demands grow, it's key to understand these principles to build resilient technical systems that users love and depend on. So here are my works cited for the talk tonight. Just want to say thank you so much for listening. Once again, big thanks to Pressable for hosting tonight's talk.
Wow, Austin, thank you so much for such an insightful talk on horizontal scaling and load balancing. Thank you all so much for coming, and we will see you at the next one.
Thank you.